Welcome to RF transceiver design course. In last class we have stopped at the low noise amplifier design. We already have discussed the amplifier design, how you can design amplifier at microwave or very high frequency for RF transceiver design. Now this is a low noise amplifier design. So while discussing the low noise amplifier design, we already discussed that what is called the input referred noise, and here in this low noise amplifier design we have make the noisy two port network to the noiseless two port network by adding the voltage source Vn and In. So this is equivalent noise voltage Vn and this is equivalent noise current In, and this is a source current Is and this is a source resistance Ys. So the noise factor can be written equal to noise power due to the source alone proportional to mean square value of a source current SC divided by a short circuit current ISC square by Is square. So now let us derive the noise factor. So what is the ISC? Means short circuit current ISC. So here current is minus Is, then plus In and Ys into Vn. So this is the total ISC short circuit current, which is minus Is plus In plus Vn Ys. If you take a mean square value of the same ISC square and the mean square, you can get a minus Is square minus Is plus In, same value you can keep it here. Now because when you try to take the square of this term, there are two multiple parameters correlated. So noise from the source and noise from the two port. So here this noise which is generated by the source, mostly it is equivalent to due to the 50 ohm or antenna impedance that is generated by the source, and noise generated by the two port network that are not correlated, it is uncorrelated. So here you can consider Is and the In and Vn Ys is equal to 0. So the correlation between Is and In plus Yn Vs equal to 0. So your mean square value of short circuit current is equal to Is square, mean square value of Is square plus the current which is In plus Vn Ys whole square. Now when you try to put this equation where the f is equal to Isc square by Is square, you will get f which is equal to 1, because Is square by Is square is equal to 1, and then In plus Vn Ys whole square by Is square. So now what is important? The relation between Vn and In, because Vn voltage generated, you have considered noise voltage of the two port network referred at the input side and noise current In, they both are correlated. So In you can divide in a two term. One is uncorrelated to the Vn, means some of the portion which is not correlated to the Vn, it is denoted as a INU, that is the uncorrelated In, and then there is a correlated to the Vn, the current In, noise current In correlated to Vn is given as a Inc. So you can write In which is equal to Inu plus Inc. Now here your Inc is given by Yc into Vn. So uncorrelated, so uncorrelated Vn, uncorrelated current Inu, that is already there, and correlated current Vn that we want to identify, that is Inc, which is a function of Yc into Vn. Now what is a Yc? So here Yc is a correlation admittance. Now we will try to put the same in the INU and INC in the previous equation, and when you multiply the In by Vn conjugate, so Vn square into In, which is equal to Yc Vn whole square. So total, then you can replace here F, which is equal to 1 plus Inu plus Vn Yc plus Ys whole square. So here in this term, initially we have only considered the Ys. So here Inu plus Inc plus Vn into Ys whole square, that we have considered here. So this Vn then Yc plus Ys, this Yc is a correlation admittance and Ys is a source admittance Ys. So Vn Yc plus Ys whole square. In this equation, what is Inu? So if you consider the conductance at the input side, then you can write the Inu, that is a 4 kT Gu into B. Gu into B, and you can write a Vn, that is due to the resistance 4 kT Rn into B. We already seen while discussing the noise current and noise voltage. So input report noise means the mean square value of noise current and mean square value of the noise voltage. So that can also be, that can directly be written 4 kT naught GUB. This is a Yc plus Ys. So Yc is given by Gc, correlation conductance Gc plus JBC, and Ys source admittance, that is BGS plus JBS. So it is a source conductance and that is a source susceptance B, that is already mentioned here. So the noise factor here, if we want to reduce the noise factor, because ultimate our aim is to design the low noise amplifier, and how we can reduce the noise. So the one of the component, means one of the parameter, if we choose a Bs equal to minus Bc in this equation, this noise factor is reduced in terms of the, this noise factor is reduced in terms of conductance G and resistance R. So again, if we want to, now here GS is a real part of Ys, and if we try to minimize noise factor, minimize, so here in this case we want to minimize the noise factor by proper selection of Ys. So if we try to minimize the noise factor, we already you can consider Bs is equal to minus Bc, and again if we want to normalize, so if we differentiate the noise factor with Gs and equate it equal to 0, we can find the value of Gs, that will give the minimum noise figure that we want. So the same equation, if you differentiate, you will get a Gu minus U by Gs square plus Rn, it can be written as a 2 Gs plus Gc minus Gs plus Gc square by Gs square, which is equal to 0, and you will get a Gs in terms of Gc. So, Gs which is equal to Gc square plus Gu by square root of Gc square by Gu by Rn. So, here value of Gs and Bs gives a source admittance Y opt. So, this is called a optimum source impedance at which you will get a minimum noise speaker F min. So, here you can replace the Gs with G opt and Bs with the B opt. So, in the previous equation what we write it down is the F min. So, minimum noise figure where F is where Ys is equal to Y opt. So, the same equation can be written as a 1 plus Gu by G opt Rn by G opt plus Gc whole square. This is where how it came? It came by considering Ys is equal to Y opt, and for that we have considered Gs which is equal to Gc square plus Gu by Rn and Bs is equal to minus Bc. So, then you can write your F. So, if you write this F in terms of F mean, you can write F mean F is equal to F mean plus Rn, that is the noise resistance Rn by Gs minus G opt square plus Bs minus B opt square. So, your F is equal to F mean plus Rn by Gs which is equal to Ys minus Y opt. So, this is nothing but the Ys and Y opt whole square, mod of Ys minus Y opt whole square. So, what is here important is if you have designed your amplifier where your source impedance Ys which is equal to optimum impedance Y opt of your amplifier, you will get the F which is equal to F mean, and Rn is a noise resistance and Gs is a conductance of the source. So, Ys you can means here small Ys is a normalized source admittance and small Y opt is a normalized optimum admittance. So, that can be given by Gs plus JBs, G opt plus JB opt. Now, we will try to use this formula. This formula is important that we have derived in order to find the minimum noise figure amplifier, means whatever noise that you want in the amplifier. So, Ys you can also write in terms of converting admittance to the reflection coefficient. You can write Ys in terms of 1 by Z naught 1 minus gamma s by 1 plus gamma s, Y opt 1 by Z naught 1 minus gamma opt by 1 plus gamma opt. Ys by Y opt you can write it by this equation, and if you consider the Gs which is real part of Ys, then it can be written as the 1 by Z naught 1 minus gamma square by 1 plus gamma s whole square. So, same equation you can also represent in terms of the reflection coefficient gamma s and reflection coefficient gamma opt. So, where f which is equal to f mean 4 Rn, here it is a Z naught. So, we have replaced Ys by Ys and Y opt, means in terms of the admittance it is a impedance now Z naught, that is the characteristics impedance, gamma s minus gamma opt whole square 1 minus gamma s square 1 plus gamma opt whole square. Now, if we try to get the fixed value of noise figure. So, if you want to design a low noise amplifier for the fixed value of a noise figure, this equation will be represented in the circles in the gamma s plane. So, how we can plot the noise circle also? You consider the noise figure parameter n. So, that noise figure parameter n which is equal to f minus f mean 4 Rn by Z naught 1 plus gamma opt, and if you put n in that equation, in this equation if you try to put the n, you will get the circle equation where gamma s minus gamma opt n plus 1 and n plus 1 minus gamma opt square by n plus 1. So, here there is a center of the circle is given by gamma opt by n plus 1. So, when what is the gamma opt? It is a optimum reflection coefficient that is provided by the manufacturer or the foundry. Your transistor should have a gamma opt at which it will provide the minimum noise figure. You can, if you are using a design kit in the simulator like a cadence or ADS, then you can if you have a multiple transistor network like cascode or differential amplifier, you can get the gamma opt from the simulator as well, where the design kit also has provided the information related to the noise parameter. So, these two parameter, one is Rn, which is a process dependent noise resistance Rn, and the gamma opt, that is also the process dependent parameter. So, gamma s minus gamma opt n plus 1, then you can get n plus 1 minus gamma opt square by n plus 1. This is the center of the circle and this is a radius of the circle. So, if you try to choose the value of gamma s is equal to gamma opt, then your noise circle means you will get a minimum noise figure, but you need to choose a gamma s which is equal to gamma opt. So, let us try to solve one problem so that we can understand the noise circles. So, same thing, S parameters at 4 gigahertz is given to us by the foundry, or you can use a simulator. This is a S parameter is provided S11, S12, S21 and S22. F mean means minimum noise figure, that is possible, that is also provided, that is 1.6 dB, that is a when you use a gamma opt which is a 0.62 angle of 100 and your noise resistance Rn is given by a 20 ohm. So, this is a parameters given by the foundry or the manufacturer of the transistor, or you can simulate it by using a cadence or Keysight ADS or any simulator, circuit simulator, where you are going to use a design kit provided by the foundry. Now, here assume device is unilateral. If you want to assume the device is unilateral, because there is already S12 is given. So, if S12 is given, or if you get the S12, if you want to use a consider it as a unilateral device, then first you need to find the unilateral figure of merit. Before that, for amplifier always the stability is also important. So, you need to do the K delta test. You can use the mu test as well. So, here K greater than 1 and delta less than 1 for your desired frequency. Now, calculate unilateral figure of merit U, that is coming as a 0.059. So, there is not much deviation between your, if you put the unilateral figure of merit in the equation of range 1 by 1 plus u square 1 by 1 minus u square, that is a 0.891 to 1.13. So, you will get this much deviation in your gain if you consider your device as a unilateral. If you do not consider it as a bilateral, then you need to use a, if you want to consider it as a bilateral, you need to follow the method that way when we have considered the bilateral amplifier design. But here you can have a flexibility in terms of the gain, means if you can have a 1 or 2 dB variation in the gain, you can go ahead with considering the unilateral figure of merit. So, here n which is equal to f minus f mean. So, you need to first find the value of n. Now, f is given to you. So, what is the f? So what is mentioned is a design an amplifier with a 2 dB of noise figure. This is a optimum minimum noise figure, but we want to design for a 2 dB of a noise figure. So f minus f mean 4 Rn by Z naught. So f you can convert into this is a noise factor. So while calculating, always remember this is a not in dB, it is absolute value. So f minus f mean divided by this is a normalized Rn by Z naught 20 by 50 ohm, and gamma opt is already given, so you can get a n. So once you find out the n, you can get the center of the noise figure circle, and then you can get the radius of the noise figure circle. So this center and radius is already given to you have find out the center of the circle and radius of the circle. Now based on this center and radius, you can plot the noise circle. We also need to plot the gain circle and noise circle together, and then you can find out the minimum noise figure. So we have already defined the S parameters, and based on the S parameter circle, S parameter we have defined the noise figure circle. Now let's take one example on the noise figure circle and how can we design the low noise amplifier by using a S parameter. So the example, we want to design a low noise amplifier at 4 gigahertz. We should have a S parameter from the foundry. If you are using a separate device like from GAN or gas foundry, if you are using a single device, based on the biasing you will get the S parameter. If you are using a design kit by using a simulator, you will get the S parameter. You also need to have a data about the gamma opt, that is optimum reflection coefficient at which you will get a minimum noise figure. So this data is also provided by the foundry, and the noise resistance Rn which is equal to 20. We will use all these parameters in order to find out the noise circles that we have discussed. So first we are assuming a device is unilateral. We need to find how much error in GT. So that is unilateral figure of merit that we can define, and that U is coming as a 0.059. And before that the first step is to find the stability at desired frequency. So here k is greater than 1, delta is less than 1. So this device is stable at this frequency based on the S parameter that is provided. Now we need to find the figure of merit, that is 1 by 1 plus u square gt by gtu 1 by 1 minus u whole square. So if you use the same equation, this it will come as a 0.891 gt minus etu 1.13. If you convert into the dB, it will be around minus 0.5 to 0.5 dB. So if there is a variation in the gain is in the range of 0.5, it is fine to consider it as a unilateral, though your device is a bilateral. We already have discussed the difference between unilateral and bilateral. So in unilateral, your S12 is considered as a 0. So here we can consider as a unilateral. Then the next step is to find the noise circles. So what is our target? Our target is design an amplifier with 2 dB of noise figure. The minimum noise figure is 1.6 dB, and we are targeting a 2 dB of noise figure. So this is for 2 dB we can get 1.58, it is absolute term, dB to absolute it is converted. Then it is f mean 1.445, Rn we already know, Z naught is 50 ohm, gamma opt is also provided. So you will find the value of n. Now this value of capital N is used in the finding this center of the noise figure circle. So this is center is a 0.56 gamma 100 and its angle is always a gamma opt. Angle is depend upon the gamma opt and this is the radius of the circle, that is a 0.24. Now if you try to draw the circle, so this is the final value, we will get n which is equal to 0.0986, CF that we will get is 0.56 angle of 100 and RF that is a 0.24. As we are designing the low noise amplifier, we need to plot the gain circle at the source side, because the LNA we are going to connect at the antenna. So, first is antenna, then LNA. So, we need to optimize the gain at the source side. So, we will plot the different gain circles for gain of 1, gain of 1.5, gain of 1.7, and it will give accordingly 0.805, 0.904 GS. So, GS is nothing but desired value of gain GS by G max, GS max. So, we will get the GS, and based on the value of GS we already discussed how to get the center of gain circle at the source side and radius of the gain circle at the source side. Now what we need to do is we need to plot both gain circle and a noise figure circle. So on the Smith chart, if you try to draw the gain circle, so you can see this line is nothing but angle that shown as a of gamma opt, and this is for the gain circle. So that depends upon the center. So what we are interested is to find the noise figure of 2 dB. So we need to make a circle which is f is equal to 2 dB, and you can see that for gamma opt you will get a minimum noise figure that is already defined. Now this 2 dB is our desired noise figure, and we need to plot the different gain circles. So you can see here gain circle for 1.7 dB, 1.5 dB and 1 dB. So as we are reducing the gain, it is the gain circles are increasing. So we need to find a point at which we will both circle, noise figure circle and gain circle will intersect with each other. So that point means it should intersect asymptotically. So here at this point it is intersecting, and that point will gives both the value, what will be the GS means gain at the source side, that is around 1.7 dB, and what is a noise figure, that is a 2 dB. So always we need to consider the circle which is a asymptotically touching, means to the uh, other gain circles. So this is a noise figure circle and gain circle, and this point we need to consider it as a gamma s, that is a 0.53 angle of 75, and you will get a gain. So you already know GL, G naught, and you will if you add all this gain, that is 1.7 dB, you will get 8.53 dB of gain. So in this what we have done, we have find out the noise figure, we have find out the based on the given parameter, we have drawn the noise figure circle, we have drawn the gain circle, and we optimize the gain at which we are getting the gamma s, which is 0.53 angle of 75. So this is how we can design the low noise amplifier. Now only the task is remain, that is to find out the, so you already have 2-port network. So this is a 2-port network. Based on the value of gamma s, you can find out the input matching network. So now you know already the gamma s value. You can use a LC matching or stub matching as per your application. and then you can make a output matching network to get the gain of 1.25 dB that we have already discussed while designing the amplifier. So, when we are designing a low noise amplifier, this gamma s, identifying the gamma s based on the noise figure circle that we have drawn. So, this is how the low noise amplifier we can design by using a S parameter method. We will discuss more about the low noise amplifier in the next class. Thank you.